So now I introduce you to Ignacio Iacobacci, who is going to talk now about pretrained language models for code understanding and generation. Well, Ignacio, I know him from quite a while. We were actually fellow PhD students when we were in Rome, at the University of Rome. And since then, actually, he's been working in many topics, and he was a senior researcher at Huawei, and now he's also a team leader there in the Noah's Ark lab in London. And yeah, he's been working in many things, like from semantics to also conversational AI, but now he's going to talk about another different thing that he's working on, that is, as I mentioned, from code understanding and generation. And yeah, without further ado, all yours.
Thank you very much. Thank you, Jose. Yeah, I know Jose for quite a while. It's always an honor to be invited to participate in this event. My name is Ignacio. Yeah, I work in Huawei Noah's Ark Lab, specifically in the speech and semantics team. So we specialize in NLP research. Even though we are working on a company, we do research. Our main objective is to do research. We publish on top-level conferences. We aim for patents, and as well we collaborate with other teams within Huawei. And I will going to present this topic, which is called Pretrained language models for code understanding and generation. This topic is really new. To be fair, so we started quite recently in our company, but also I have seen that the research community, at least the NLP research community, has been not working on this topic that much. Last ACL I saw 8 papers talking about this, so it's quite new. So I hope you enjoy it and you can ask a lot of questions. Okay, this is more or less the context of the talk. We'll start with why code, why we work on this. So there is estimation that there are 27 million software developers in the world. That number is growing year by year. So at the end of 2024, we expect to have more, like almost 29 million software developers. That number will keep to increase. We don't expect to all the people become software developers eventually, so we need to help, because everything is based on software, we need to start helping the software developers to do code more efficiently and quickly and in a better way. Also, doing software development is not easy. The software developer use one of the 50 active programming languages. As you can see, there is a list of most popular languages. So a few years ago, when I was a software engineer, I used to use Java. Then I migrated to Python. Now Python is really popular. JavaScript is also popular. C, C#, and the variants are still there. Some languages that are old but refuse to die, like COBOL or Fortran. So yeah, there's a lot of things happening there, and there's always the need of keeping support to this to the code developed back then. We have also estimations that in the last 20 years, 2.8 trillion lines of code has been coded. So that's a lot. And probably most of that code is buggy. There's probably no documentation whatsoever, or it's bad documentation, or it's lost, or it's not updated. So yeah, everything can be. So it's really difficult to deal with code as software engineers. No, not quite well. There's an obvious need to help to automatize some of the process of software development and improving the software quality. But Okay, let's stop speaking about code. So this is a talk about natural language processing. So the idea is to approach the problem of code understanding generation using natural language approaches. How difficult, how different they are. So from the book Compilers, Principles, Techniques and Tools from AHO and others, a programming language are notations for describing computations to people and machines. A program needs to be, in order to be run, needs to be translated into a form that can be executed by a computer. And that's the most fundamental difference between natural language and programming language. Language is a way to communicate between humans, but programming language is something that we, in some sense, communicate with machines, but machines need to execute, right? A few differences between natural language and programming languages. As already mentioned, natural language is something that we created to be interpreted by humans to understand each other. Programming language is something that we code and eventually needs to be interpreted by a machine. We can read code, but it's not the main objective of the code. For those that are familiar with assembly, it's far from being interpreted by humans. Natural language is ambiguous. It's a way to be efficient in communication for humans, but it's not a desirable feature while programming. So programming languages are by definition not ambiguous. Natural language has, for historical reasons, for how natural language evolves, polysemy, has words that have many meanings and depending on the context can mean different things. In programming languages there's no polysemy. There are words, protected keywords for instance, are words that in any context means the same depending on the language, def or class. It's always the way that we define a function, or we define the first word to define a class. So there's no polysemy whatsoever. Natural language is dynamic. It evolves because it changes over time. Programming languages, well, there have different versions of the programming language, but different versions of a programming language can be seen as a different language itself. And natural language has some structure, but is flexible because at the end, the objective of the natural language is to communicate. Programming language is defined as a grammar, and the grammar is unflexible. As I mentioned also, natural programming languages from source code, from the code we as humans create, needs to be converted. Happens like many steps in order to be created or converted into a different representation that can be in fact executed by a computer. It's analyzed by a lexical analyzer, then a syntax analyzer, there's a type checker, there's a semantic analysis as well, there's a translator, and eventually that generates code which, depending on the way the code will be executed, can be either machine code, which is shown here, or it can be a bytecode, something that itself runs in a different program, can be a source code that is interpreted or is created. It converts into a different programming language that is, again, converted and executed into a program. So it highly depends how the source code is executed, but these different steps from the source code to the machine code that can be executed has a lot of information that I will show later can be used to make a system that can easily or more efficiently interpret and understand code. And maybe the final fundamental difference between programming languages and natural language is, for natural language, there's no easy way to know if something we say it's accurate or not. We struggle a lot to have human annotators to know if something that generates language generates something in an accurate way or not. For programming languages, it's not the case. So a program needs to be executed, but we do have a way to know if the program works or not. It's actually generated properly or not. We can check if the syntax is correct, and the syntax is unique and needs to follow a grammar, but needs to be executed, and we have unit tests to test the functionality of the program itself. And that's a strong signal in this, maybe the main difference compared to natural language, and we use that a lot and I will mention a lot in the following slides how to approach how to use that information in creating code. Okay, that's the problem. How to approach this problem? So code has been approaching many different ways, from natural language processing and from deep learning and even ancient machine learning approaches. Lately, from the introduction of pre-trained language models, very deep and large language models, we have seen that these language models can be used for approaching code as well. A little bit of background. If you are not familiar, this is an NLP workshop. Everything is based on transformers right now. So yeah, a transformer is a structure. It's a deep learning model for code, for natural language understanding and generation. Has this architecture that has many layers and can use relies on attention to be able to understand a large piece of text. It replaced the old SDMs, which replaced again word-to-vec approaches. And the idea is you put text on the inputs. Each input is divided into tokens, which are words of subwords, and are combined to have a contextual representation for each token, which is a word or subword, from the input. And from that, we can generate an output, which is, again, a text. Transformers have been used in NLP in two different flavors, let's say. So when I refer to models or BERT-like models, are models that has been trained on this mass language modeling training, and it's basically a model that is able to learn semantic representations of the input, and the whole point is to create a nice vector representation. While the GPT models are models that are trained like reading the input from left to right, and are trained in order to predict what's the next word. That's kind of the commonly known language models. Right now, those models are called causal language models because there's a causality of the next word given the previous context. Those are the two flavors, and the first flavor, so the BERT-like models, are generally more associated with understanding, while the second one are the perfect fit for generation tasks. And transformers can have many variants. XLMR models are models that can understand many different languages. They are trained on either parallel data or trained with many sources with many raw data from many languages. Text-to-text transformer, or called T5, is a model that is trained on the objective of tasks that can be defined as a sequence-to-sequence task. So either define the task, translate this sentence, and the output should be the sentence in the objective language, or if you have a task which is the question answering, the input is the question and the expected output is the answer. If you are, you can use summarization as well as a sequence-to-sequence task. You give a large text and you expect to have a reduced text that means the same or represent the same thoughts, etc. Electra, so a model that is used in a discriminative objective in order to train the language model, or BART that also trains a model into a kind of, let's say, denoising input. So inputs a noise version of the input and then generates the entire sentence token by token. That's are a few, maybe the most known models that are used on natural language. And we train pre-trained language model for NLP in that way. So we get a large text corpus, a few gigabytes. The largest data set right now is the pile. I don't know if you hear about that. Are 800 gigabytes of raw text. I think it's compressed, so probably larger. And you put into a model and you train until, well, never converge, but you train a few days on many GPUs, and you get a model that can be then fine-tuned, or maybe just doing some few shot or zero-shot training on different tasks regarding to NLP. Text classification, NER, QA, etc. Currently doing with programming languages. The main difference is, in addition or instead of training the model with natural language, we input the model code snippets or chunks of code or entire classes, and use different, depending on the model, similar or slightly different train objectives, and we train a model based on that. And then those models, which have the capability to understand the language, can be then fine-tuned on different tasks for code understanding and generation. I listed a few. I will speak slightly, so I will speak later some of the tasks, some of the data set that can be approached with these models. Okay, data sets are really important. So I mentioned the pile. For natural language, it's the largest, or what's the largest? Maybe there's a largest one now. But where to get training for these kind of models? Has been a challenge that was presented in 2019 that was then used as a training data for the earlier versions of these pre-trained language models for code understanding. This was this challenge, which released a data set which was called CodeSearchNet, contained 99 natural language queries, which and the main objective of that was to be associated into the actual code that was related to the query. So if there was a problem definition or a code snippet, not a code snippet, a doctrine or something that described a functionality, and the objective was to associate or to relate or find the most similar, in some sense, piece of code to the query. And this data set was quite large, 6 million functions from 6 different programming languages, and the idea was to relate or choose among the right answer among almost 1,000 destructors. So that was a quite challenging task, and this data was also then used for creating models. Okay, we can. Okay, let's pretend we know how to relate code and language. What's the next step? CONCODE wanted to created a data set. CONCODE is a data set, so they created a data set for doing code generation. So given a query, given a description of a functionality, the idea for this data set was to create a class in Java language that implements that functionality. So it was really ambitious. So it was basically the task of source code understanding, and was provided a natural language documentation, so the class definition, but the source code generation was conditioned to the class environment. So what was the functionality required? There was other information provided in the data set. This data set CONCODE was also used for training different models. The output for in this data set, the output of any model to approach code generation was evaluated in terms of exact match or BLEU score. For those which are not familiar with the BLEU score, so exact match is exactly what is the reference of the class definition. BLEU score is a metric commonly used for natural language generation, which counts the amount of unigrams, bigrams, trigrams, and fourgrams that are similar to the proposed solution. Proposed solution, or in case of generation, the goal, the main goal of the generation. That's problematic because we know that in code we can create a solution, a working solution, a piece of code that provides the same functionality but looks completely different. In order to alleviate that, CodeBLEU was introduced. CodeBLEU recognized that that BLEU is not enough to evaluate the generation of code in terms of the amount of n-grams that are similar to the proposed solution, and they also do an evaluation in terms of the syntactic structure of the generated code and the semanticality of the code. So if a code has different variable names, so there will not be any overlap in terms of tokens, but semantically those variables represent the same because maybe are just a variable renaming. So CodeBLEU takes into account that as well. Also this AST, so it's the abstract syntax tree of the code. If the code seems to perform the same task, so the flow of information is going in the same direction, even though the code looks different in some sense, that also can be recognized by this syntax tree. And CodeBLEU, what it does is to do a weighted average of these three different ways to see the code, and that was shown that this was CodeBLEU is a more useful metric than just BLEU for understanding if a piece of code automatically generated was near to the correct one or the proposed one or not. And then CodexGlue happened. CodexGlue was presented last year. So they took some of the datasets, the existing datasets, for instance, CONCODE and CodeSearchNet are part of that, and they added, so you can see in blue, or you see green here, but in blue it's there were new tasks that they introduced in this set of tasks. CodeBLEU is a benchmark for code understanding and generation, and they propose these tasks, and the main objective was to create approach individually or approach all the tasks all together with a single model. That was the main idea of the benchmark. As you can see, in the column named as baselines, there are a set of model names. The models are there because depending on the task, the model that is needed to approach the task is slightly different. As I mentioned there, so the task can be roughly divided into generation and understanding. We can maybe, if we go to the main definition of each task, clone detection, so checking if two pieces of code are cloned one of the other one, we can arguably understand that it's a task for code understanding. So I'm giving a score, maybe a similarity score, or a 1-0 value, checking if the two pieces of code are one clone of the other one or not. Defect detection seems to be a classification task, given a piece of code, trying to understand if the piece of code is buggy or not. Close test is also the same, so I remove, there's a keyword or a function name or some variable name removed from a code, and the objective is to recreate, to fill the blank on that code. Those tasks can be easily approached with a model that looks like BERT. That's why the baseline is annotated as CodeBERT. For other tasks, the objective is to generate something. So given an existing input, I need to either complete what is missing or create a different representation from the input I have. Those are the tasks for code completion. So I have a piece of code is not finished, and I need to complete it based on a code description that it has the half-done code, code repair. So it might be arguably similar to what we saw in the first talk. Given a piece of code which is buggy, instead of detecting if the piece of code is buggy or not, give a piece of code that is all the bugs has been removed. Code translation, similar to machine translation, given a piece of code in one programming language, Java, C, C++, I want to have the same functionality, the same code in a different language. Code search, we mentioned it before. Code summarization, which is the task of giving a piece of code, giving a natural language description of what the code is doing, which can be either high level or low level. So either line by line what the code is doing, or doing a proper summarization. What is the main task the code is solving? And maybe the most important task of among all of these, text-to-code generation, which is kind of the main purpose of these models, and the task which was not so far was really challenging to approach it with any other model. Well, this is something I already mentioned. So these two tasks can be divided into understanding and generation. Depending on the task, you either need a model that can be understand and generate a semantic representation, which is eventually fine-tuned for classification or a regression task or generation, even an input generate something else. Lately, has been introduced this data set called Eval. Eval was introduced in the paper evaluation large language model trained from code. So this is the same paper which introduced Codex, and Codex is what OpenAI Codex is used for GitHub Copilot. I will speak about that later. Eval is really interesting. It's really tiny, so it's 164 programming problems. Was manually crafted or probably modified from, manually modified from existing problems, and are just that, problems for, so there's a problem definition, there's a set of unit tests that the code needs to solve, and the code snippet that solves the problem. That's pretty much it. And yeah, the difference compared to the text-to-code generation task from CodexGlue. CodexGlue is evaluated in terms of CodeBLEU or exact match. Eval is evaluated in terms of unit tests. So I don't care how your code that is generated looks like. I want to perform the task I'm expecting. In the same, so using the same idea, so another data set slightly larger than Eval was released. There are a few more data sets. I'm covering the most important benchmarks that are used right now. Mostly basic programming problems. It contains 900 short Python programs constructed from crowdsourcing. And all the problems contains a description and a set of unit tests, or in this case, asserts. So you can run the asserts and check if the solution, the proposed solution, runs the asserts or not. The good thing about MPPP that there are problems that include numerical manipulation to tasks that are more difficult to solve, that require some non-trivial external knowledge. In this case, it's called, it's required to solve, to implement merge sort, which is a common application for sorting a list. You need to know what is that algorithm. Sometimes the model, the problems are even more, so it require even more deep knowledge. So solve this equation or try to calculate the numerical derivation of a polynomial function. Unless you know, you are aware what's a derivative, the model will not be able to solve that problem. Okay. I will cover a few models that has been released for code understanding and how we approach this aspect. So the most trivial thing to do for code understanding was basically what was released in 2020. Canada et al. Released CODEBERT, which is Code Understanding BERT. It's just BERT trained on code. They grab a data set from Python source code and train a model with the same train objective of BERT, but using instead of raw text data, the code data from Python. That was the easiest thing to do, the most trivial one, and obviously it's not the greatest. Not the best in any sense. I think we can do it slightly better because, okay, we have the code, but generally, in addition to code, we have the code description. We have a docstring. That's what CodeBERT does. In addition to the snippet, the code snippet, use the training signal as an extra input. So both the code and the natural language are trained together in a model that is uses or reuses the same idea that how the model called Electra, so I mentioned it a few slides before, was used. So the basic idea is I get the input, I mask some of the tokens of the input, and the model, which is a discriminator model, needs to understand if the models that are, which is the generator and the for natural language and code, replace the token which was masked to a different token. That's the objective, the training objective, and so Electra was really good for natural language, and CodeBERT was also slightly better than QBERT. Well, and CodeBERT was also trained for not only Python, but Python, Java, JavaScript, and other languages as well. Something we have seen on code models that similarly happens with the multilingual models. Training on different programming languages does help, and also because there's a lot of overlap among different programming languages, that also is kind of maybe more obvious than compared to natural languages. Okay, so I mentioned that we use the code snippet as a training signal. We add the docstring, so the natural language as input. We can go one step further and say, okay, what about adding another modality, another training signal? That's what GraphCodeBERT does. So in addition to code and the text, they include an extra, let's say modality, let's call it modality or queue from the code. So they model the data flow of information from the variables on the code. And they change the training objective. So in addition to the masked language model that was used for training the text and the code, they use data flow edge prediction to check, so to predict this graph structure from the data flow graph. And another training objective which was related the identifiers, so the variables from the code to the data flow sequence they have in the other modality input. This model was even better than CodeBERT. So it seems that adding more richer input does help. Can we go one step further? Sure we can. SyncoBERT, which was developed by some colleagues of mine from Huawei as well, so that the data flow was a nice training signal, but we can go one step further and say, okay, what happens if we add the abstract syntax tree representation from the code in addition to the source code and the docstring? And they use different training objectives. So in addition to the masked language model, they use identifier prediction. So trying to understand among all the tokens in the source code input, which ones constitute a variable, and also doing edge prediction among the abstract syntax tree. And in addition to that training objective, they use contrastive learning between the different modalities. So trying to relate as near as possible to create the representations as near as possible from the docstring and the code snippet, the docstring and the abstract syntax tree, etc. and this was proven to be even better than all the three previous models. Finally, CodeGPT was yet another model presented by a colleague of mine. They extended the idea presented in the previous model in SyncoBERT. If adding different modalities helps, what happens if we add even more useful information as the input? So they included the code snippet, they included the natural language, they included both the after syntax tree and the data flow graph from GraphCodeBERT. And in addition, they created different views of the code, doing function on variable renaming, or changing loops by changing like fors with ifs, or rewriting the code, keeping the functionality, or doing dead code insertions that change slightly the structure of the code but not the what the code does, and using that and training that with again a contrastive learning objective that was proving to be even better than even the previous model. We can see here, so all the models I named and a few others are here. So CodeBERT, GraphCodeBERT, so all the models. If you add a new function, a new modality, a new richer input, the model keeps improving. Okay. Clock is ticking. Okay, let me briefly mention models that are approaching generation. So far, I mentioned models that are specifically designed for code understanding. So the main objective is to create a semantic representation of code. For generation, we need to create code based on some modality as input. The more basic model, which was released with the CodexGlue benchmark, was called CodeGPT. Basically, a GPT model trained on code, as simple as possible. Was trained on Java and Python, and the most interesting thing about this model was they trained two different versions. One was trained from scratch, and one was trained after being trained on like GPT, on raw data, on raw text. The main difference is the vocabulary used for the model trained from scratch, using extensively the whole transformer architecture, so not only the decoder but also the encoder. PLBART can be seen as a natural extension of the BART model, or any model that do sequence-to-sequence prediction, and thus was trained or in a kind of a multilingual representation. So given an input, the output was to generate the same input but filling the missing words with blanks, so filling the blanks from the input on different natural language and programming languages. And then the model was fine-tuned to specific tasks as summarization or code generation or code translation. But those are these three tasks: summarization, generation, and translation. This was okay. It was not a bad model, but this model was superseded by CodeDeFi. It's similar, so both architectures of CodeDeFi and PLBART use an encoder-decoder transformer. Uses again a denoising sequence-to-sequence pre-training, using masked spam prediction, identifier tagging, and masked identifier prediction. So the differences are there, but basically, so if you have an input, you need to fill which are which masked words which masked word correspond to which names. So demask the inputs. Also using this identifier tagging, so given the input, identify as a sequence-to-sequence task, which was the which input corresponds to a variable identifier or not. And this bimodal dual generation, which was given a description, generate the code, and given the code, generate the description. Including all these training objective was even better than doing the kind of simplest thing done by PLBART. For generation, this is the last model I will mention. Encoder is really interesting because, contrary to the other two models, the main idea of encoder was to generate code snippets or chunks of code, but in filling the model, the code, right? So instead of creating a chunk of code at the end, so they replace some of the code or the docstring from the input with a mask, and they train the model to complete what was masked and allowing more than one token to replace that chunk. That model was really interesting. Maybe it's not the best model for doing code generation, but certainly this infilling method it was a really nice idea and improved. And also the model was released as public, which is problematic, and most of the models are not. Okay. So these are, so far we talk about the kind of more researchy models which has been presented. But as I mentioned, the most important thing, most important task to solve right now is code completion and program synthesis. Why is that? We are not sure, but there are many companies trying to get their own AI helper for programming. There might be something, maybe money, I'm not completely sure. But there are many companies, there's a lot of interest on creating an automatic programmer, an AI-based programmer. And many companies, they release their own. OpenAI released Codex. This model is based on GPT-3, so it's a decoder model. Was trained with 159 gigabytes of Python code after being trained so it's based on CodeGPT, but after the raw text data was trained on code. And that's the building block for GitHub Copilot. They train different models in terms of sizes, the largest one being this 12 billion parameter model, and that's really, really good. And they also release a data set, which is human Eval, I mentioned before, and a numerical stable estimation for passed K, which is the way we do the evaluation if the generation is successful or not. So they managed to create this metric for that. And in addition, they released two other models called CodexS and CodexD, which were fine-tuned for code generation based on the kind of in-domain code generation problems, and CodexD, which was created for or fine-tuned for code summarization, for creating descriptions from code. The answer from Google, from DeepMind to Codex was AlphaCode, which was basically the same model. It's also a GPT-like model. Was not trained on Python only, but many different programming languages, and using up to more than 700 gigabytes of code in addition to raw data. and they created and trained models which are like larger than the previous codex, being the largest one 41 billion parameters, so it was significantly large. And the main objective of AlphaCode, they didn't want to compare codex, but to approach the prompt synthesis. So they, in addition to the code they use, they gather information from like code competitions, like code context, and they fine-tune the model on that. And the way they generated the code was to, well, they trained the model, they fine-tuned on these code context solutions, and given a new problem, they generated 1,000, 10,000 different versions of the solution. They cluster those solutions, and they check if the solutions were working similarly. So if given a different set of inputs, the behavior was similar. So that was the way they clustered the solutions. And the most popular cluster was chosen as the most probable solution. And they were able to, so this model was evaluated in terms of the code context, like trying to pretend to be a person on code context, and was, they argue, they say that it was behaving as an average parameter. I'm not completely sure if that's true, but let's give that as granted. And finally, the last model I want to mention is the model released by Salesforce. Again, a model which is also based on GPT architecture. The main difference compared to the other two models is that they take the prompt synthesis as a conversational paradigm. So instead of giving a prompt definition, they expect to have a code. This way to generate code is taken as a dialogue. So there's a nice demo you can see from the Salesforce page. But given a problem definition, they generate a snippet, and you can refine that definition by writing something else. And the program is able to either recall what has been coded so far, taking into consideration the previous solution, the previous description of the problem. This model was trained again with a really large amount of data, up more than 1 terabyte of training data in both in natural language and code, and they train a model up to 16 billion parameters. So it's not the largest model, but it's the largest in terms of the amount of data they use for training. So these are, there are more, but these are the most, let's say, known models for code generation that has been released, or not released, nothing is released, but introduced by different companies. Okay, to conclude, well, there's a tremendous interest on automatizing code understanding and generation. There's a lot of money involved, so that makes sense. Natural language and programming languages are similar, but not that much. So it's always is important to know, to be aware of the differences. Nevertheless, we can see that similar approaches that work from natural languages can be applied to programming languages and work. There's a ton of lines of code array to be used. So just most of these models are just trained on scrapping GitHub and other Git repositories. Yeah, many tasks for understanding generation can be approached using pretrained language models. The most important task, or this is the gold rush, let's say, speaking of idioms, is on text-to-code generation. That's the most important task, at least so far right now. And this task was not able to be approached a few years ago. It's far from being solved, but we are trying so at least we have something to work on. So far, the things that work are training with more data, going bigger, doing over-generation and filtering. That's not enough. We cannot escalate, so okay, let's use a data center, we cannot use 10 in 6 months, so we need to have better ideas and better models, and well, it's up to you so, to be interested in this topic and maybe to propose new ideas and new models for that. That's pretty much it. Thank you very much.